All right, welcome. In this video, I want to talk a little bit about different sizes of infinity, and we usually call these countable infinite and uncountable infinite. So these ideas were first introduced by a mathematician named Georg Cantor in the 1800s. And he was the first to able to show that there are different sizes of infinities. Some infinities are bigger than others. And the method he used to show this was a new kind of proof technique called diagonalization. So let's start with just exploring these ideas of infinities based on what we maybe already know about the size of certain infinite sets. So in particular, we know that, for instance, we can take the set of odd numbers and add them to the set of even numbers. If we have all the odd numbers and we take them and we union them, say, to the set of even numbers, we're going to get the natural numbers, which is all of our normal counting numbers. Each of these sets is of infinite size. There are infinite odd numbers, there are infinite even numbers, and there are infinite natural numbers. So we get this strange, interesting equation here that says infinity plus infinity equals infinity. You may have already explored some of these equations, maybe in calculus and so on, and realize that sometimes infinity plus infinity equals infinity, but sometimes it might be something different, or maybe not in the addition case, but maybe in a subtraction case. Sometimes infinity minus infinity is still infinity. So for instance, if we take all the natural numbers and we subtract out the even numbers, which is an infinite subset, we still have an infinite subset left over. So we might have infinity minus infinity and equals infinity. So these, when we start taking infinity and putting them into arithmetic like this, it starts being a little bit confusing. They don't seem to follow the same rules as our normal finite numbers do. So this is interesting. This raises a question: are the natural numbers bigger than the even or the odd numbers, or are they the same size, as maybe this equation might tell us? So what Cantor helped us do is show that these sets were all the same size, and he did this by using a kind of relation or function called a bijection. And if you remember, a bijection is a relationship between two sets that is both one-to-one and onto. What this means is that every member of one set is going to be paired up with a member of the other set. So we can imagine them all lining up in a big long line. Let's start with the natural numbers here, 0, 1, 2, 3, 4, and so on. We know that all of the natural numbers will be on this line, but that this line is ultimately infinite in length. So they'll all be there, but it is infinitely long. Now, let's do a quick exploration here. Are all the even numbers going to show up on this line? Sure enough, they are. We have 0, 2, 4, 6, 8. We have all of the even numbers here. They're all going to show up as well. And because we've got them in this sort of line, in this table rather, we've got them paired up. We can see exactly which natural number each of these even numbers should be paired up with. And we can imagine, we can even skip down, what is the even number 1,000,000, what is it going to be paired up with? Well, it looks like it will be paired up with the natural number that is exactly half its size, so maybe 500,000 or 500,000. Likewise, we've paired up all the odd numbers with the natural numbers as well, also with the even numbers if we like, showing that all three of these sets are going to be the same length because all three of them can be lined up, and each member of the even set would have a specific member of the natural number set that they are paired with and a specific member of the odd set that they are paired with. So instance 8 here is paired with 4 and 9, and because every single number will have one and only one member from the other set, that's the definition of a bijection, or what we've just expressed there is both one-to-one and onto. So we're saying that exactly every member of, say, the even number set will have exactly one pair from the natural numbers. This is how we know they're paired up. This is how we know that they have the same size. If every member of the set can be paired up with another member of the other set, they must have the same size. Again, this was the insight that Cantor provided us with, which gave us the tools now that we can start comparing the sizes of infinite sets and finding that indeed some of them are going to be the same size, maybe counter to our intuition. So it is with this idea that Cantor can define his idea of countable infinite. So an infinite set is said to be countable if it has the same size as the natural numbers. And again, there's this sort of natural interpretation here that's saying it's countable because we can put them on this list of natural numbers. We can say this is the first one, this is the second one, this is the third one. That's what we mean by countable. So any set, any infinite set that can be put in this list and we don't miss any members when we do it, we will say is countable. So as I've sort of expressed, our tool for showing things are uncountable is, can we put them on a list? That's the strategy. Can we put them on one list? So using this idea, we can show, for instance, that the integers, so the integers, the natural numbers were bigger than the even numbers and odd numbers, at least in an appearance at first glance. Likewise, the integers seem to maybe be twice as big as the naturals because we have all the naturals and then we have all the negative naturals. But that's the same relationship that we had with evens and odds. Twice as big didn't make us any bigger, so probably not here either. And sure enough, we can show that the integers can all be listed on one list by just alternating between the positive values and the negative values. And that will make sure that every single integer will appear on this list. And again, with this strategy, we can probably go ahead and guess, well, where is, integer number 1 million going to be stored? Well, it looks like it's going to be half minus 1, so 499,999 should be paired up with 1 million, and then 500,000 should be paired up with negative 1 million. So we can figure out, every single integer, what its possible pair would be, and therefore we can put them all on this list, and therefore they are also countable. The number of integers is countable. So let's consider a different set now. We're trying to expand things a little bit more. So here I'm actually interested in a case where I'm going to pick all the pairs of numbers. So the way in set theory, the way we would do this is we would say, let's take the cross product of the natural numbers with itself, which will give us pairs of natural numbers n and m. Okay, when we take the cross product, we typically end up by multiplying the size of our set. Our set gets bigger. So in this case, we have infinity times infinity. And again, our expectation here is this is still equal to infinity, but there's, I guess, a question mark. Is it the same infinity? Is it countable or not? Can we still put them on one list? So let's think about these pairs. If we have all the pairs and we put them all onto one list, well, we haven't really figured out how to put them on one list yet, but what I can do is I can put them in this table. I can put all infinity of them in this two-dimensional table where, for instance, we have all the 0, 0, 0, 0, 1, 0, 2, 0, 3, for instance, this row. Now, one thing we'll notice here is if we try and put all these elements into a list, if we naively try and go row by row, we try and put all the ones on the first row in first, there are actually infinity of them on that row. We will not finish that row before we get to the next row. That seems to be an argument that we cannot put these all on a list. There's just infinity of them on just one of these lists, so we'll probably run out. And the same thing goes if we go column by column. If we try and put this first column first, there are infinity in that column, and we will never get to starting the second column. We will put all of them on there. So there is this sense that maybe we have finally found a set that is larger than the natural numbers. Turns out this is not true because we can indeed go diagonal by diagonal, and I've kind of colored them out here with my rainbow colors a little bit to sort of show what this would be like. We basically do the 0, 0 first, then we do the 1, 0 and the 0, 1, then the 2, 0, 1, 1 and 0, 2. One thing we will notice if we look at the sum of the numbers in this diagonal, they all sum to 2. If we look at the sum of the numbers in this diagonal, they all sum to 3, all sum to 4, all sum to 5. By going in this order, it's true every diagonal gets one longer than the last one, but no diagonal is infinite in length, and that means that we will hit every single diagonal. We will hit every single number in this table if we go diagonal by diagonal, and therefore we can indeed list them all. So what this means is the set of all pairs of numbers, n and m, is also countable. And we can extend this to triples and quadruples and so on. So triples of numbers or quadruples of numbers are also countable. Okay, so an interesting, again, maybe countering our intuition. Now, why did I want to look at pairs of numbers? Well, the reason I wanted to look at that is because I want to talk about the rational numbers. Those are all numbers that can be written as a natural number p over a natural number q, or an integer p over an integer q if we want the positive and negative rational numbers. And in this case, we can see that every rational number can be seen as a pair of natural numbers, a numerator and a denominator. Not all of those result in in different fractions, I should say. For instance, 0 over 1 equals 0 over 2 equals 0 over 3. So some of those fractions are repeated in these pairs. But since we know the set of pairs is countable, therefore the set of fractions, rational ratios of numbers, must also be countable. So we know that the rational numbers are indeed countable numbers. So let's now focus on the real numbers. Can we put the real numbers all on one list? And spoilers, no, we can't. This is what Cantor helped us show, that this set is what we would call uncountably infinite, and therefore is larger than the set of natural numbers. So here's just an idea. This isn't sort of a proof. This is just a rough idea to show why it's a little bit tricky. In the natural numbers, if you select any two numbers, n and m, and then you figure out all of the numbers between them, there's only going to be some finite number between them. So between any two numbers in the natural numbers, there are only a finite numbers. If you do this with the real numbers, if you select any two numbers, n and m, then you ask how many numbers are there between these two numbers in the real set. There are always still infinite numbers between them. So for instance, if you take the numbers 0 and 1, how many numbers are there between them? There are infinite. If you now pick a smaller one, the numbers 0 and 0.1, there are still infinite between them. If you pick the numbers 0 and 0.0000000000001, there are still infinite numbers between them. So no matter how small you try and put those two numbers together, there are still infinite numbers between them. This is, in the real numbers, what we call an interval of real numbers. It's like there's this continuum of real numbers that go between these 2 points, and you can never make that continuum be not a continuum. It never be not just sort of a single number or just a single element without reducing this interval all the way down to just one number. Now, what that also means is the reason why this doesn't show up as a proof for us is this is also true of the rational numbers. And we just showed that the rational numbers are indeed countably infinite. So just because we have this weird, take any two of them, how many are there in between, they're still infinite, that doesn't necessarily imply that we're uncountable. But this is a very interesting property of the real numbers, also of the rational numbers, that we're going to highlight. Now, I've got some notation here. You may have encountered this interval notation before, that on the real numbers, because there is a infinite number between there, we like to express that set, or that range is usually what we call it, by using just indicating the beginning and the end point for that particular range. So n to m here. Now we also use square or round braces to say whether we include the boundary point. So this is, the square braces mean inclusive, so this means n up to m but including n and including m. This means n up to m but not including n and not including m. And then we can combine them together, so not including n and including m, or including n and not including m. These are just a notation for intervals. Quick refresher in case you forgot that. Okay, so we're going to now argue, I'm going to do a proof, but it's going to be a little bit informal, that the set of real numbers is uncountable. And this proof is going to rely on this new technique called diagonalization, so I'm going to point it out as we go. So again, let's use this interval notation to focus our proof on just this set here. So just the set of numbers, or the interval of numbers between 0 and 1. And here I'm indicating I'm including 0, but I'm not including 1. And that's not super important, other than that what we're trying to do is get numbers that are 0 point something. That's what we want, 0 point something. We're only going to focus on the something part that comes after the 0, or after the decimal, I should say. We could extend this argument to other numbers, another range, a different range other than this range. This is just going to be the easiest range to focus on, so we're going to focus on that range. I'll mention that if this little part of the real numbers is uncountable, then that means the whole set of real numbers must be uncountable. That maybe makes sense. If if a subpart is uncountable, then the whole thing must be uncountable. Okay, so why did we want to focus in on this particular range? I told you I want to focus on all the numbers that can be written 0 dot. Well, that means in binary, I'm going to assume we're in binary for the moment, it's just a little simpler. Then that means we're just going to have this series of bits that come off afterwards, B1, B2, B3, and this series will be infinite long. For real numbers, we need an infinite long string. Maybe for rational numbers, there would be some point where we could cut them off and maybe just have zeros after that point or something like that. But in these in the real numbers, we're going to have to account for infinite non-repeating numbers. For instance, the irrational numbers are going to be in there as well. So we're going to want to make sure we can account for those. Well, again, the only thing that I'm highlighting here, every number in our interval can be written like this: a 0, then a decimal, and then infinite bits. Okay, so the proofs by diagonalization are embedded within a proof by contradiction, effectively. We're going to say, assume that we do have a countable set. That means that this set of numbers that we've got here can be put on a list. And in particular, let's imagine what that list is going to look like. Here we are assuming it's countable, so we're using the principle or the definition of countability to say there must be a list, but we don't necessarily know what that list is. So I'm just going to call them R1, R2, R3, etc. And here I've got an example of what the list might look like, but it doesn't matter. I don't care which numbers actually show up as R1 or R2 or R3. Whatever list works, that's the list I want to focus on. But we can imagine writing them down. We might have this first one, blah, blah, blah. It's an infinite string of bits. We have this second one. It's a different infinite string of bits. That's the only important bit, is they have to be different from each other. And we'll just assume that we've put every single one on this list. Again, starting one and going up to infinity, we'll assume they're there. Now, we're going for a contradiction here. Our goal is to try and show that this is not possible, and our goal to do that is we're going to try and show that there's at least one number on this list that or rather there's at least one number that should be on this list that isn't. And here's how we're going to do it. So we're going to use this technique called diagonalization to try and build a number D. We're going to call it D for a diagonal, and we're going to state what each of the bits are of D to try and show that D is not going to be equal to Ri. So Ri, remember, is the ith number on our bit. And we want to show that D is not equal to Ri for every single Ri. Okay, now the way we're going to do this is we're going to be very special. We're going to go to the first Ri, R1 here, and we're going to take its first bit after the decimal point here, and we're going to look at it. In this case, in my example, it was a 0, but we're just going to flip it. So our definition here is the ith bit of D, in this case the first bit of D, is going to be the first bit of the first number on our list, but negated. So we take 0, we're going to flip it 1. Now what that means is, if you'll notice, D here starts 0.1, but R1 starts 0.0. So after this step, we know that D is not equal to R1 because it's not equal on this one bit. Okay, so this one bit is different, so we know we're not equal to R1. So now what do? We go to R2. I want to be different from R2 as well. So I can't set my first bit. I've already picked my first bit to make sure that I'm not the same as R1. So I'm going to move down to the second bit. My second bit, I look at the second bit of the second R. I see it's a 0. Again, I flip my bit. I make my bit 1. So that I guarantee I'm now not equal to R2. And I keep doing this. I go down the whole infinite list. I say I'm not equal to R3. I'm not equal to R4. And I've flipped exactly one bit of every single one of these numbers that I guarantee that D is not on this list. So what we will say is that this number D, this is a diagonalizer. It diagonalizes against the list by ensuring it's not equal to any one of these numbers on the list, by making sure it's not equal to the one bit that is in the diagonal, and making sure that we can then guarantee that we are not equal to any number on our list, therefore D's not on our list. Now that's a contradiction. okay, D should be on our list. We know it's not because of this bit difference, so now we've arrived at the contradiction. We assumed that this list could exist because we assumed we were countable, but then we showed that the list was incomplete. And again, we don't know which list it was. We didn't make up the list. We just said we can take any list you give us and we can find this number D that's not on the list, and therefore those lists cannot possibly even exist. There is no such list of all the real numbers. So that's our conclusion then, that the set of real numbers is uncountable. And that leaves us in an interesting space, which is we have these three statements or theorems. The size of the natural numbers is infinite. The size of the real numbers is infinite. But the size of the natural numbers is smaller than the size of the real numbers. These are all three things that are true, which means there must be some infinities that are smaller than other infinities. So to accommodate these new kinds of infinities, these new sizes, we need new symbols. We can't just use infinity, the infinity symbol, for all of them. So we've introduced this new kind of notation. It's called the Aleph notation. Aleph is a Hebrew letter, and that's the Hebrew letter there. Kind of looks like a stylized X or H maybe. And the Aleph null or Aleph 0 is defined to be the size of the natural numbers. So the first infinity is the countable infinity, or the counting numbers infinity, where you just go 0, 1, 2, and it just keeps going. That's the size of Aleph null, the size of the natural numbers. In the Aleph notation, we then have other Alephs. We have Aleph 1. That is the next largest infinity, bigger than Aleph 0. And we can define a sequence of Alephs now. Aleph 1, Aleph 2, Aleph 3, and so on. These are the infinities as they get bigger and bigger from one another. Okay. Now, we believe that it's possible that Aleph 1 is the size of the real numbers. But we can't prove that within the set theory that we have. Happens to be a Gödel sentence, at least I believe, meaning that this is one of the sentences that is true or false within the axioms of set theory, but we cannot prove that it is true or false within the axioms of set theory, because the set theory is incomplete thanks to Gödel. And that means that we have to assert that it is true or false instead. So there is a thesis or hypothesis, or you could call it an axiom if you like. It's called the continuum hypothesis, that just asserts that Aleph 1 is the size of the real numbers. What this is saying is there are no infinities between the size of the natural numbers and the size of the real numbers. Now, again, this is just an assertion. We are saying this is true without proving it is true. Someone could equally validly just say it's false and say this is not true. There are other infinities, and it's possible that at some point in the future of mathematics, we may have a need to talk about different infinities between Aleph 0 and Aleph 1, at which point we may abandon the continuum hypothesis. However, it doesn't seem to make a big difference to a lot of us right now whether this is true or not. So if you want to believe in the continuum hypothesis as well, you're welcome to do that. All right, so there is a corollary that comes out of some of these proofs that we've done here. And this is related to binary strings. So the first one is the set of binary strings is countable, and I think that one is pretty easy to argue. And if you, I'll leave it as an exercise for maybe you to argue that yourself. Remember, all you're going to need to do is show that the set of finite strings can be put on a list, but the set of infinite binary strings is uncountable. That just is a result of what we just proved. The real number that we were looking at was 0 point and then an infinite binary string. And what we really showed is that those infinite binary strings cannot be put on a list. And so what that means is the set of infinite binary strings is uncountable. And again, this results to us in two interesting theorems. I'm going to do a quick hand-wavy proof of these theorems. The first one is the set of Turing machines is countable. How do we argue that? Well, recall that a Turing machine can be encoded as a finite length binary string. So when I gave a definition of what a Turing machine could be, I said that a Turing machine is a 7-tuple, and it was written over some alphabet. We'll talk about this in another video in more detail, but we can take that 7-tuple that we've written formally as a string of symbols and convert it into binary. And if we do that, then we can quite easily argue that that set is countable. As I already mentioned, the set of binary strings is countable, and finite binary strings, I should say, is countable. So since every Turing machine corresponds to a finite length binary string, and the set of finite binary strings is countable, therefore the set of Turing machines must also be countable. Okay, so why is that relevant to us? Well, I can argue, and I will now, that the set of languages is uncountable. So the number of languages there are is uncountable. The number of Turing machines there are is countable. That's going to result in a very interesting conclusion for us. But let's prove this bit. The set of languages is uncountable. So a language by itself is a set of finite length binary strings. So like, is epsilon in the language, is 0 in the language, is 1 in the language, and so on. We can say the language is just a collection or a subset of these finite length binary strings. Since the set of finite length binary strings is countable, we already argued that, we can put them all on a list. And for simplicity, we usually do that in order of size. There's a canonical ordering. We put epsilon first, then 0, then 1, then 0, 0, then 0, 1, then 1, 0, then 1, 1, and so on. There's this canonical ordering of them, so it's pretty easy for us to argue that they're countable, so we'll put them in this list. Now, thinking about our language, for each one of these strings, our language is either going to say, yes, this string is in my language, or no, this string is not in my language. Like, for instance, if our language is the even length strings, it will say, it'll find all the even length ones and say, yes, these ones are in it. And it will say all the odd length ones, no, these ones are not in it. Okay, so what that means is we can imagine going down the list of binary strings, starting with epsilon and then 0 and then 1 and so on, and just assigning a bit. If it's in the language, we say it's a 1, and if it's not in the language, we'll assign a 0. So what that means is this language corresponds to an infinite length binary string. Okay, so every infinite length binary string corresponds to a distinct language and vice versa. So there's a one-to-one and onto relationship between the infinite length binary strings and the number of languages. So we know that these two are the same size. But we've argued in Cantor's proof that we've just looked at that the set of infinite length binary strings is uncountable. So this means the set of languages must also be uncountable. Okay, so what does this result in? This means there must be a language that is not, well, here I'm expressing it as that is not recognizable, but what we really mean is imagine trying to pair up Turing machines with languages. Well, there is uncountable languages and there are countable Turing machines, so there must be some languages that don't get paired up with Turing machines. That must mean there are some languages that cannot be recognized by a Turing machine or cannot be decided by a Turing machine is another corollary, which means that we have languages that cannot be computed or cannot be decided. And this is a very important conclusion. And in our next video, we're going to explore a little bit, can we identify one such language or more than one such language? So thanks a lot for watching. We'll see you in that next video.